An image is shown of a rocket that appears to have just passed through a layer of clouds as it travels skyward. A bright white light is seen in the upper right corner of the image. To the lower left appears the layer of clouds and the bottom of the rocket with fire projecting from the fuel cones at its base. Figure 4.1. Many modern rocket fuels are solid mixtures of substances combined in carefully measured amounts and ignited to yield a thrust-generating chemical reaction. Credit: Modification of work by NASA. Chapter outline. 4.1 Writing and balancing chemical equations. 4.2 Classifying chemical reactions. 4.3 Reaction stoichiometry. 4.5 Quantitative chemical analysis. Solid fuel rockets are a central feature in the world's space exploration programs, including the new Space Launch System being developed by the National Aeronautics and Space Administration (NASA). To replace the engines of these rockets rely on carefully prepared solid mixtures of chemicals combined in precisely measured amounts. Igniting the mixture initiates a vigorous chemical reaction that rapidly generates large amounts of gaseous products. These gases are ejected from the rocket engine through its nozzle, providing the thrust needed to propel heavy payloads into space. Both the nature of this chemical reaction and the relationships between the amounts of the substances being consumed and produced by the reaction are critically important considerations that determine the success of the technology. This chapter will describe how to symbolize chemical reactions using chemical equations, how to classify some common chemical reactions by identifying patterns of reactivity, and how to determine the quantitative relations between the amounts of substances involved in chemical reactions, that is, the reaction stoichiometry. Learning objectives. By the end of this section, you will be able to derive chemical equations from narrative descriptions of chemical reactions, write and balance chemical equations in molecular, total ionic, and net ionic formats. An earlier chapter of this text introduced the use of element symbols to represent individual atoms. When atoms gain or lose electrons to yield ions, or combine with other atoms to form molecules, their symbols are modified or combined to generate chemical formulas that appropriately represent these species. Extending this symbolism to represent both the identities and the relative quantities of substances undergoing a chemical or physical change involves writing and balancing a chemical equation. Consider as an example the reaction between one methane molecule, CH4, and two diatomic oxygen molecules, O2, to produce one carbon dioxide molecule, CO2, and two water molecules, H2O. The chemical equation representing this process is provided in the upper half of Figure 4.2, with space-filling molecular models shown in the lower half of the figure. This figure shows a balanced chemical equation followed below by a representation of the equation using space-filling models. The equation reads CH subscript 4 plus 2O subscript 2 arrow, CO subscript 2 plus 2H subscript 2O. Under the CH subscript 4, the molecule is shown with a central black sphere, representing a C atom, to which four smaller white spheres, representing H atoms, are distributed evenly around. All four H atoms are bonded to the central black C atom. This is followed by a plus sign. Under the 2O subscript 2, two molecules are shown. The molecules are each composed of two red spheres bonded together. The red spheres represent O atoms. To the right of an arrow, and under the CO subscript 2 appears a single molecule with a black central sphere with two red spheres bonded to the left and right. Following a plus sign and under the 2H subscript 2O are two molecules, each with a central red sphere and two smaller white spheres attached to the lower right and lower left sides of the central red sphere. Note that in space-filling models of molecules, spheres appear slightly compressed in regions where there is a bond between two atoms. Figure 4.2. The reaction between methane and oxygen to yield carbon dioxide and water, shown at bottom, may be represented by a chemical equation using formulas top. This example illustrates the fundamental aspects of any chemical equation. The substances undergoing reaction are called reactants, and their formulas are placed on the left side of the equation. The substances generated by the reaction are called products, and their formulas are placed on the right side of the equation. plus signs, plus separate individual reactant and product formulas, and an arrow separates the reactant and product, left and right sides of the equation. The relative numbers of reactant and product species are represented by coefficients, numbers placed immediately to the left of each formula. A coefficient of 1 is typically omitted. It is common practice to use the smallest possible whole number coefficients in a chemical equation, as is done in this example. Realize, however, that these coefficients represent the relative numbers of reactants and products, and therefore they may be correctly interpreted as ratios. Methane and oxygen react to yield carbon dioxide and water in a 1:2, 1:2 ratio. This ratio is satisfied if the numbers of these molecules are, respectively, 1:2:1:2, or 2:4:2:4, or 3:6:3:6, and so on. Figure 4.3. Likewise, these coefficients may be interpreted with regard to any amount number unit, and so this equation may be correctly read in many ways, including: 1 methane molecule and 2 oxygen molecules react to yield 1 carbon dioxide molecule and 2 water molecules. 1 dozen methane molecules and 2 dozen oxygen molecules react to yield 1 dozen carbon dioxide molecules and 2 dozen water molecules. 1 mole of methane molecules and 2 moles of oxygen molecules react to yield 1 mole of carbon dioxide molecules and 2 moles of water molecules. Figure 4.3. Regardless of the absolute numbers of molecules involved, the ratios between numbers of molecules of each species that react, the reactants, and molecules of each species that form, the products, are the same and are given by the chemical reaction equation. Balancing equations. The chemical equation described in section 4.1 is balanced, meaning that equal numbers of atoms for each element involved in the reaction are represented on the reactant and product sides. This is a requirement the equation must satisfy to be consistent with the law of conservation of matter. It may be confirmed by simply summing the numbers of atoms on either side of the arrow, and comparing these sums to ensure they are equal. Note that the number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that element by the element's subscript in the formula. If an element appears in more than one formula on a given side of the equation, the number of atoms represented in each must be computed and then added together. For example, both product species in the example reaction, CO2 and H2O, contain the element oxygen, and so the number of oxygen atoms on the product side of the equation is 1 CO2 molecule times 2 O atoms CO2 molecule plus 2 H2O molecules times 1 O atom H2O molecule equals 4 O atoms. The equation for the reaction between methane and oxygen to yield carbon dioxide and water is confirmed to be balanced per this approach, as shown here. CH4 plus 2O2, 2CO2 plus 2H2O. Element reactants products balanced? C1 times 1 equals 1. 1 times 1 equals 1. 1 equals 1. Yes. H4 times 1 equals 4. 2 times 2 equals 4. 4 equals 4. Yes. O 2 times 2 equals 4. 1 times 2 plus 2 times 1 equals 4. 4 equals 4. Yes. A balanced chemical equation often may be derived from a qualitative description of some chemical reaction by a fairly simple approach, known as balancing by inspection. Consider as an example the decomposition of water to yield molecular hydrogen and oxygen. This process is represented qualitatively by an unbalanced chemical equation, H2, O to H2 plus O2, unbalanced. Comparing the number of H and O atoms on either side of this equation confirms its imbalance. Element reactants products balanced? H1 times 2 equals 2, 1, times 2 equals 2, 2 equals 2, yes, O, 1, times 1 equals 1, 1, times 2 equals 2, 1 does not equal 2, no. The numbers of H atoms on the reactant and product sides of the equation are equal, but the numbers of O atoms are not. To achieve balance, The coefficients of the equation may be changed as needed. Keep in mind, of course, that the formula subscripts define, in part, the identity of the substance, and so these cannot be changed without altering the qualitative meaning of the equation. For example, changing the reactant formula from H2O to H2O2 would yield balance in the number of atoms, but doing so also changes the reactant's identity. It's now hydrogen peroxide and not water. The O-atom balance may be achieved by changing the coefficient for H2O to 2, 2H2O to H2 plus O2 unbalanced. Element. Reactants products balanced. H2 times 2 equals 4, 1 times 2 equals 2, 4 does not equal 2, no, O2 times 1 equals 2, 1 times 2 equals 2, 2 equals 2, yes. The H-atom balance was upset by this change, but it is easily re-established by changing the coefficient for the H2 product to 2. 2H2, O to 2H2 plus O2, balanced. Element reactants products balanced. H2 times 2 equals 4. 2 times 2 equals 4, 4 equals 4, yes? O2 times 1 equals 2, 1. Times 2 equals 2, 2 equals 2, yes. These coefficients yield equal numbers of both H and O atoms on the reactant and product sides, and the balanced equation is, therefore, 2H2, O2 2H2 plus O2. Example 4.1. Balancing chemical equations. Write a balanced equation for the reaction of molecular nitrogen N2 and oxygen O2 to form dinitrogen pentoxide. Solution. First, write the unbalanced equation. N2 plus O2 to N2O5 unbalanced. Next, count the number of each type of atom present in the unbalanced equation. Element reactants products balanced? N1 times 2 equals 2, 1 times 2 equals 2, 2 equals 2, yes. O1 times 2 equals 2, 1 times 5 equals 5. 2 does not equal 5, no. Though nitrogen is balanced, changes in coefficients are needed to balance the number of oxygen atoms. To balance the number of oxygen atoms, a reasonable first attempt would be to change the coefficients for the O2 and N2O5 to integers that will yield 10 O atoms, the least common multiple for the O atom subscripts in these two formulas. N2 plus 5O2 to 2 N2O5 unbalanced. Element reactants products balanced. N1 times 2 equals 2, 2 times 2 equals 4, 2 does not equal 4, no. O 5 times 2 equals 10, 2 times 5 equals 10, 1 O equals 10, yes. The N-atom balance has been upset by this change. It is restored by changing the coefficient for the reactant N2 to 2. 2N2 plus 5O2 to 2N2O5. Element reactants products balanced? N2 times 2 equals 4. 2 times 2 equals 4. 4 equals 4, yes. O5 times 2 equals 10. 2 times 5 equals 10. 10 equals 10, yes. The numbers of N and O atoms on either side of the equation are now equal, and so the equation is balanced. Check your learning. Write a balanced equation for the decomposition of ammonium nitrate to form molecular nitrogen, molecular oxygen, and water. Hint: balance oxygen last, since it is present in more than one molecule on the right side of the equation. Answer: 2 New Hampshire 4NO3 to 2N2 plus O2 plus 4H2O. It is sometimes convenient to use fractions instead of integers as intermediate coefficients in the process of balancing a chemical equation. When balance is achieved, all the equation's coefficients may then be multiplied by a whole number to convert the fractional coefficients to integers without upsetting the atom balance. For example, consider the reaction of ethane C2H6 with oxygen to yield H2O and CO2, represented by the unbalanced equation C2H6 plus O2 to H2O plus CO2, unbalanced. Following the usual inspection approach, one might first balance C and H atoms by changing the coefficients for the two product species, as shown. C2H6 plus O2 to 3 H2O plus 2 CO2, unbalanced. This results in 7 O atoms on the product side of the equation, an odd number. No integer coefficient can be used with the O2 reactant to yield an odd number, so a fractional coefficient, 72, is used instead to yield a provisional balanced equation. C2H6 plus 7 2O2 to 3 H2O plus 2 CO2. A conventional balanced equation with integer-only coefficients is derived by multiplying each coefficient by 2. 2C2H6 plus 7O2 to 6H2O plus 4 CO2. Finally, with regard to balanced equations, recall that convention dictates use of the smallest whole number coefficients. Although the equation for the reaction between molecular nitrogen and molecular hydrogen to produce ammonia is indeed balanced, 3N2 plus 9H2 to 6 New Hampshire 3. The coefficients are not the smallest possible integers representing the relative numbers of reactant and product molecules. Dividing each coefficient by the greatest common factor, 3, gives the preferred equation. N2 plus 3H 2 to 2 New Hampshire 3. Link to learning. Use this interactive tutorial for additional practice balancing equations. Additional information in chemical equations. The physical states of reactants and products in chemical equations very often are indicated with a parenthetical abbreviation following the formulas. Common abbreviations include S for solids, L for liquids, G for gases, and AQ for substances dissolved in water. Aqueous solutions as introduced in the preceding chapter. These notations are illustrated in the example equation here. 2NaS plus 2H2OL 2NaOHAQ plus H2G. This equation represents the reaction that takes place when sodium metal is placed in water. The solid sodium reacts with liquid water to produce molecular hydrogen gas, and the ionic compound sodium hydroxide, a solid in pure form but readily dissolved in water. Special conditions necessary for a reaction are sometimes designated by writing a word or symbol above or below the equation's arrow. For example, a reaction carried out by heating may be indicated by the uppercase Greek letter delta over the arrow. CaCO 3S delta CaOs plus CO2G. Other examples of these special conditions will be encountered in more depth in later chapters. Equations for ionic reactions. Given the abundance of water on Earth, it stands to reason that a great many chemical reactions take place in aqueous media. When ions are involved in these reactions, the chemical equations may be written with various levels of detail appropriate to their intended use. To illustrate this, consider a reaction between ionic compounds taking place in an aqueous solution. When aqueous solutions of calcium chloride and silver 1 nitrate are mixed, a reaction takes place producing aqueous calcium nitrate and solid silver 1 chloride. CaCl2 plus 2 silver 1 nitrate AQ calcium nitrate 2 AQ plus 2 AgCls. This balanced equation, derived in the usual fashion, is called a molecular equation because it doesn't explicitly represent the ionic species that are present in solution. When ionic compounds dissolve in water, they may dissociate into their constituent ions, which are subsequently dispersed homogeneously throughout the resulting solution. A thorough discussion of this important process is provided in the chapter on solutions. Ionic compounds dissolved in water are, therefore, more realistically represented as dissociated ions in this case. CaCl2 AQ to Ca2 plus AQ plus 2 Cl minus AQ 2 silver 1 nitrate AQ to 2 Ag plus AQ plus 2 NO3 minus AQ calcium nitrate 2 AQ to Ca2 plus AQ plus 2 NO3 minus AQ. Unlike these three ionic compounds, silver 1 chloride does not dissolve in water to a significant extent, as signified by its physical state notation, This. Explicitly representing all dissolved ions results in a complete ionic equation, In this particular case, the formulas for the dissolved ionic compounds are replaced by formulas for their dissociated ions. Ca2 plus Aq plus 2Cl minus Aq plus 2Aq plus 2NO3 minus Aq plus 2NO3 minus Aq plus 2NO3 minus Aq plus 2 AgCls. Examining this equation shows that two chemical species are present in identical form on both sides of the arrow, Ca2 plus Aq and NO3 minus Aq. These spectator ions whose presence is required to maintain charge neutrality, are neither chemically nor physically changed by the process, and so they may be eliminated from the equation to yield a more succinct representation called a net ionic equation. Ca2 plus Aq plus 2Cl minus Aq plus 2 AgCl. Following the convention of using the smallest possible integers as coefficients, this equation is then written. These molecular and complete ionic equations provide additional information, namely, the ionic compounds used as sources of Cl- and Ag+. Example 4.2. Ionic and molecular equations. When carbon dioxide is dissolved in an aqueous solution of sodium hydroxide, the mixture reacts to yield aqueous sodium carbonate and liquid water. Write balanced molecular, complete ionic, and net ionic equations for this process. Solution. Begin by identifying formulas for the reactants and products and arranging them properly in chemical equation form. CO2 Aq plus NaOH Aq to Na2CO3 Aq plus H2OL unbalanced. Balance is achieved easily in this case by changing the coefficient for NaOH to 2, resulting in the molecular equation for this reaction. CO2 Aq plus 2 NaOH Aq to Na2CO3 Aq plus H2OL. The two dissolved ionic compounds, NaOH and Na2CO3, can be represented as dissociated ions to yield the complete ionic equation. CO2 Aq plus 2Na plus Aq plus 2OH minus Aq to 2Na plus Aq plus CO32 minus Aq plus H2OL. Finally, identify the spectator ions, in this case Na plus Aq, and remove it from each side of the equation to generate the net ionic equation. CO2 Aq plus 2Na plus Aq plus 2OH minus Aq to 2Na plus Aq plus CO32 minus Aq plus 2OH minus Aq plus 2OH minus Aq to CO32 minus. Check your learning. Diatomic chlorine and sodium hydroxide, Li, are commodity chemicals produced in large quantities along with diatomic hydrogen via the electrolysis of brine, according to the following unbalanced equation. Sodium chloride Aq plus H2OL minus 2 minus electricity NaOH Aq plus H2G plus Cl2G. Write balanced molecular, complete ionic, and net ionic equations for this process. Answer: 2 sodium chloride Aq plus 2 H2OL to 2 NaOH Aq plus H2G plus Cl2G molecular. 2 Na plus Aq plus 2 Cl minus Aq plus 2 H2OL to 2 Na plus Aq plus 2 OH minus Aq plus H2G plus Cl2G complete ionic. 2 Cl minus Aq plus 2 H2OL to 2 OH minus Aq plus H2G plus Cl2G net ionic. Learning objectives. By the end of this section, you will be able to define 3 common types of chemical reactions: precipitation, acid-base, and oxidation reduction. Classify chemical reactions as one of these 3 types given appropriate: descriptions or chemical equations. Identify common acids and bases. Predict the solubility of common inorganic compounds by using solubility rules. Compute the oxidation states for elements and compounds. Humans interact with one another in various and complex ways. and we classify these interactions according to common patterns of behavior. When two humans exchange information, we say they are communicating. When they exchange blows with their fists or feet, we say they are fighting. Faced with a wide range of varied interactions between chemical substances, scientists have likewise found it convenient, or even necessary, to classify chemical interactions by identifying common patterns of reactivity. This module will provide an introduction to three of the most prevalent types of chemical reactions: precipitation, acid-base, and oxidation reduction. Precipitation reactions and solubility rules. A precipitation reaction is one in which dissolved substances react to form one or more solid products. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution and are sometimes referred to as double displacement, double replacement, or metathesis reactions. These reactions are common in nature and are responsible for the formation of coral reefs in ocean waters and kidney stones in animals. They are used widely in industry for production of a number of commodity and specialty chemicals. Precipitation reactions also play a central role in many chemical analysis techniques, including spot tests used to identify metal ions and gravimetric methods for determining the composition of matter. See the last module of this chapter. The extent to which a substance may be dissolved in water or any solvent is quantitatively expressed as its solubility, defined as the maximum concentration of a substance that can be achieved under specified conditions. Substances with relatively large solubilities are said to be soluble. A substance will precipitate when solution conditions are such that its concentration exceeds its solubility. Substances with relatively low solubilities are said to be insoluble, and these are the substances that readily precipitate from solution. More information on these important concepts is provided in a later chapter on solutions. For purposes of predicting the identities of solids formed by precipitation reactions, one may simply refer to patterns of solubility that have been observed for many ionic compounds. Table 4.1. Soluble ionic compounds contain these ions exceptions: NH4+, group I, cations, Li+, Na+, K+, Rb+, Cs+, none, Cl-, bridge, bridge, DAC, compounds with Ag+, Hg22+, and Pb2+, F compounds with group 2 metal cations, Pb2+, and Fe3+, C2 hydrogen oxide HCO3 Number 3. ClO3 none. SO42 compounds with Ag+, Ba2+, Ca2+, Hg22+, Pb2+, and Sr2+. Insoluble ionic compounds contain these ions. Exceptions: CO32-, CrO42, PO43, S2-, compounds with group 1 cactose, and New Hampshire 4+, OH compounds with group 1 cations and Ba2+. Table 4.1. A vivid example of precipitation is observed when solutions of potassium iodide and lead nitrate are mixed, resulting in the formation of solid lead iodide. 2KiAq plus lead 1 nitrate 2Aq to PBI2S plus 2 potassium nitrate Aq. This observation is consistent with the solubility guidelines. The only insoluble compound among all those involved is lead iodide, one of the exceptions to the general solubility of iodide salts. The net ionic equation representing this reaction is Pb2 plus Aq plus 2I minus Aq to PBI2S. Lead iodide is a bright yellow solid that was formerly used as an artist's pigment known as iodine yellow, figure 4.4. The properties of pure lead-2 iodide crystals make them useful for fabrication of X-ray and gamma-ray detectors. A photograph is shown of a yellow-green opaque substance swirled through a clear, colorless liquid in a test tube. Figure 4.4a. Precipitative lead-2 iodide forms when solutions containing Pb2+ and I- are mixed. Credit: Der Criolla / Wikimedia Commons. The solubility guidelines in Table 4.1 may be used to predict whether a precipitation reaction will occur when solutions of soluble ionic compounds are mixed together. One merely needs to identify all the ions present in the solution and then consider if possible cation/anion pairing could result in an insoluble compound. For example, mixing solutions of silver nitrate and sodium chloride will yield a solution containing Ag+, NO3-, Na+, and Cl- ions. Aside from the two ionic compounds originally present in the solutions, silver 1 nitrate and sodium chloride, two additional ionic compounds may be derived from this collection of ions, NaO3 and silver 1 chloride. The solubility guidelines indicate all nitrate salts are soluble, but that silver 1 chloride is one of insoluble. A precipitation reaction, therefore, is predicted to occur as described by the following equations. Sodium chloride Aq plus silver 1 nitrate Aq AgClS plus NaO3 Aq molecular Ag plus Aq plus Cl minus Aq AgClS net ionic. Example 4.3. Predicting precipitation reactions. Predict the result of mixing reasonably concentrated solutions of the following ionic compounds. If precipitation is expected, write a balanced net ionic equation for the reaction. A. Potassium sulfate and barium nitrate. B. Lithium chloride and silver acetate. C. Lead nitrate and ammonium carbonate. Solution. A. The two possible products for this combination are KNO3 and barium sulfate. The solubility guidelines indicate barium sulfate is insoluble, and so a precipitation reaction is expected. The net ionic equation for this reaction, derived in the manner detailed in the previous module, is Ba2 plus Aq plus SO2 minus 4 Aq barium sulfate Sb. The two possible products for this combination are LiC2, H3O2, and silver 1 chloride. The solubility guidelines indicate silver 1 chloride is insoluble, and so a precipitation reaction is expected. The net ionic equation for this reaction, derived in the manner detailed in the previous module, is Ag plus, Aq plus, Cl minus, Aq AgClS, C. The two possible products for this combination are lead-2 carbonate and NH4NO3. The solubility guidelines indicate lead-2 carbonate is insoluble, and so a precipitation reaction is expected. The net ionic equation for this reaction, derived in the manner detailed in the previous module, is Pb2 plus Aq plus CO2 minus 3 Aq lead-2 carbonate S. Check your learning. Which solution could be used to precipitate the barium ion Ba2+ in a water sample, sodium chloride, sodium hydroxide, or sodium sulfate? What is the formula for the expected precipitate? Answer: sodium sulfate, barium sulfate. Acid-base reactions. An acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. Such reactions are of central importance to numerous natural and technological processes, ranging from the chemical transformations that take place within cells in the lakes and oceans, to the industrial-scale production of fertilizers, pharmaceuticals, and other substances essential to society. The subject of acid-base chemistry, therefore, is worthy of thorough discussion, and a full chapter is devoted to this topic later in the text. For purposes of this brief introduction, we will consider only the more common types of acid-base reactions that take place in aqueous solutions. In this context, an acid is a substance that will dissolve in water to yield hydronium ions, H3O+. As an example, consider the equation shown here. HClAq plus H2OlCl minus Aq plus H3O plus Aq. The process represented by this equation confirms that hydrogen chloride is an acid. When dissolved in water, H3O+ ions are produced by a chemical reaction in which H+ ions are transferred from HCl molecules to H2O molecules, figure 4.5. The process represented by this equation confirms that hydrogen chloride is an acid. When dissolved in water, H3O+ ions are produced by a chemical reaction in which H+ ions are transferred from HCl molecules to H2O molecules, Figure 4.5. This figure shows two flasks labeled A and B. The flasks are both sealed with stoppers and are nearly 3/4 full of a liquid. Flask A is labeled HCl followed by G in parentheses. In the liquid, there are approximately 20 space-filling molecular models composed of one red sphere and two smaller attached white spheres. The label H subscript 2O followed by a Q in parentheses is connected with a line to one of these models. In the space above the liquid in the flask, four space-filling molecular models composed of one larger green sphere to which a smaller white sphere is bonded are shown. To one of these models, the label HCl followed by G in parentheses is attached with a line segment. An arrow is drawn from the space above the liquid pointing down into the liquid below. Flask B is labeled H subscript 3O superscript positive sign followed by a Q in parentheses. This is followed by a plus sign and Cl superscript negative sign, which is also followed by a Q in parentheses. In this flask, no molecules are shown in the open space above the liquid. A label, Cl superscript negative sign followed by a Q in parentheses, is connected with a line segment to a green sphere. This sphere is surrounded by four molecules composed each of one red sphere and two white smaller spheres. A few of these same molecules appear separate from the green spheres in the liquid. A line segment connects one of them to the label H subscript 2O, which is followed by L in parentheses. There are a few molecules formed from one central larger red sphere to which three smaller white spheres are bonded. A line segment is drawn from one of these to the label H subscript 3O superscript positive sign, followed by a Q in parentheses. Figure 4.5. When hydrogen chloride gas dissolves in water, it reacts as an acid, transferring protons to water molecules to yield B, hydronium ions, and solvated chloride ions. The nature of HCl is such that its reaction with water, as just described, is essentially 100% efficient. Virtually every HCl molecule that dissolves in water will undergo this reaction. Acids that completely react in this fashion are called strong acids, and HCl is one among just a handful of common acid compounds that are classified as strong, Table 4.2. A far greater number of compounds behave as weak acids and only partially react with water, leaving a large majority of dissolved molecules in their original form and generating a relatively small amount of hydronium ions. Weak acids are commonly encountered in nature, being the substances partly responsible for the tangy taste of citrus fruits, the stinging sensation of insect bites, and the unpleasant smells associated with body odor. A familiar example of a weak acid is acetic acid, the main ingredient in food vinegars. CH3 Colorado 2 HAQ plus H2OL rightwards harpoon over leftwards harpoon, CH3CO2 minus AQ plus H3O plus AQ. When dissolved in water under typical conditions, only about 1% of acetic acid molecules are present in the ionized form, CH3CO2 minus. Figure 4.6. The use of a double arrow in the equation above denotes the partial reaction aspect of this process, a concept addressed fully in the chapters on chemical equilibrium. This figure contains two images, each with an associated structural formula provided in the lower left corner of the image. The first image is a photograph of a variety of thinly sliced, circular cross-sections of citrus fruits, ranging in color from green to yellow, to orange and reddish-orange. The slices are closely packed on a white background. The structural formula with this picture shows a central chain of 5 C atoms. The leftmost C atom has an O atom double bonded above and to the left, and a singly bonded O atom below and to the left. This single bonded O atom has an H atom indicated in red on its left side, which is highlighted in pink. The second C atom moving to the right has H atoms bonded above and below. The third C atom has a single bonded O atom above, which has an H atom on its right. This third C atom has a C atom bonded below it, which has an O atom double bonded below and to the left, and a singly bonded O atom below and to the right. An H atom appears in red and is highlighted in pink to the right of the singly bonded O atom. The fourth C atom has H atoms bonded above and below. The fifth C atom is at the right end of the structure. It has an O atom double bonded above and to the right, and a singly bonded O atom below and to the right. This single bonded O atom has a red H atom on its right side, which is highlighted in pink. The second image is a photograph of bottles of vinegar. The bottles are labeled balsamic vinegar and appear to be clear and colorless. The liquid in this bottle appears to be brown. The structural formula that appears with this image shows a chain of two C atoms. The leftmost C atom has H atoms bonded above, below, and to the left. The C atom on the right has a doubly bonded O atom above and to the right, and a singly bonded O atom below and to the right. This O atom has an H atom bonded to its right, which is highlighted in pink. Figure 4.6a. Fruits such as oranges, lemons, and grapefruit contain the weak acid citric acid. B. Vinegars contain the weak acid acetic acid. Credit A. Modification of work by Scott Bauer. Credit B. Modification of work by Brooke Osteropa. Common strong acids. Compound formula name in aqueous solution. HBr hydrobromic acid. HCl hydrochloric acid. HNO3 nitric acid. Hydrogen hypochlorite perchloric acid. H2SO4 sulfuric acid. Table 4.2. A base is a substance. The most common bases are ionic compounds composed of alkali or alkaline earth metal cations, groups 1 and 2, combined with the hydroxide ion, for example, NaOH and calcium hydroxide. Unlike the acid compounds discussed previously, these compounds do not react chemically with water. Instead, they dissolve and dissociate, releasing hydroxide ions directly into the solution. For example, KOH and barium hydroxide dissolve in water and dissociate completely to produce cations K+ and Ba2+, respectively, and hydroxide ions OH-. These bases, along with other hydroxides that completely dissociate in water, are considered strong bases. Consider as an example the dissolution of Li, sodium hydroxide, in water. NaOH's Na plus Aq plus OH minus Aq. This equation confirms that sodium hydroxide is a base. When dissolved in water, NaOH dissociates to yield Na plus and OH minus ions. This is also true for any other ionic compound containing hydroxide ions. Since the dissociation process is essentially complete when ionic compounds dissolve in water under typical conditions, NaOH and other ionic hydroxides are all classified as strong bases. Unlike ionic hydroxides, some compounds produce hydroxide ions when dissolved by chemically reacting with water molecules. In all cases, these compounds react only partially and so are classified as weak bases. These types of compounds are also abundant in nature and important commodities in various technologies. For example, global production of the weak base ammonia is typically well over 100 million metric tons annually, being widely used as an agricultural fertilizer, a raw material for chemical synthesis of other compounds, and an active ingredient in household cleaners. Figure 4.7. When dissolved in water, ammonia reacts partially to yield hydroxide ions, as shown here. NH3Aq plus H2OL, rightwards harpoon over leftwards harpoon, New Hampshire 4, plus Aq plus OH minus Aq. This is, by definition, an acid-base reaction, in this case involving the transfer of H+ ions from water molecules to ammonia molecules. Under typical conditions, only about 1% of the dissolved ammonia is present as New Hampshire 4+ ions. This photograph shows a large agricultural tractor in a field, pulling a field sprayer and a large white cylindrical tank, which is labeled Caution Ammonia. Figure 4.7. Ammonia is a weak base used in a variety of applications. A. Pure ammonia is commonly applied as an agricultural fertilizer. B. Dilute solutions of ammonia are effective household cleansers. Credit A. Modification of work by National Resources Conservation Service. Credit B. Modification of work by PAT 00139. A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and a base, but not water, and the products are often a salt and water, acid plus base salt plus water. To illustrate a neutralization reaction, Consider what happens when a typical antacid, such as milk of magnesia. Note that in addition to water, this reaction produces a salt, magnesium chloride. Example 4.4. Writing equations for acid-base reactions. Write balanced chemical equations for the acid-base reactions described here. A. The weak acid hydrogen hypochlorite reacts with water. B. A solution of barium hydroxide is neutralized with a solution of nitric acid. Solution. A. The two reactants are provided, HOCl and H2O. Since the substance is reported to be an acid, its reaction with water will involve the transfer of H+ from HOCl to H2O to generate hydronium ions, H3O+, and hypochlorite ions, OCl-. HOClAQ plus H2OL rightwards harpoon over leftwards harpoon OCl- AQ plus H3O plus AQ. A double arrow is appropriate in this equation because it indicates the HOCl is a weak acid that has not reacted completely. B. The two reactants are provided, barium hydroxide and HNO3. Since this is a neutralization reaction, the two products will be water and a salt composed of the cation of the ionic hydroxide, Ba2+, and the anion generated when the acid transfers its hydrogen ion, NO3-. BaOH2AQ plus 2HNO3AQ barium nitrate 2AQ plus 2H2OL. Check your learning. Write the net ionic equation representing the neutralization of any strong acid with an ionic hydroxide. Hint: consider the ions produced when a strong acid is dissolved in water. Answer: H3O plus AQ plus OH minus AQ 2H2OL. Chemistry in everyday life. Stomach antacids. Our stomachs contain a solution of roughly 0.03 mHCl, which helps us digest the food we eat. The burning sensation associated with heartburn is a result of the acid of the stomach leaking through the muscular valve at the top of the stomach into the lower reaches of the esophagus. The lining of the esophagus is not protected from the corrosive effects of stomach acid the way the lining of the stomach is, and the results can be very painful. When we have heartburn, it feels better if we reduce the excess acid in the esophagus by taking an antacid. As you may have guessed, antacids are bases. One of the most common antacids is calcium carbonate. The reaction: KCO3S plus 2HClAQ rightwards harpoon over leftwards harpoon CaCl2AQ plus H2OL plus CO2G. Not only neutralizes stomach acid, it also produces CO2G, which may result in a satisfying belch. Milk of magnesia is a suspension of the sparingly soluble base magnesium hydroxide. It works according to the reaction: magnesium hydroxide 2S rightwards harpoon over leftwards harpoon Mg2 plus AQ plus 2OH minus AQ. The hydroxide ions generated in this equilibrium then go on to react with the hydronium ions from the stomach acid, so that H3O plus OH minus rightwards harpoon over leftwards harpoon 2H2OL. This reaction does not produce carbon dioxide, but magnesium contains. Several antacids have aluminum hydroxide, AlOH3, as an active ingredient. The aluminum hydroxide tends to cause constipation, and some antacids use aluminum hydroxide in concert with magnesium hydroxide to balance the side effects of the two substances. Chemistry in everyday life. Culinary aspects of chemistry. Examples of acid-base chemistry are abundant in the culinary world. One example is the use of baking soda, or sodium bicarbonate in baking. Sodium hydrogen carbonate is a base. When it reacts with an acid such as lemon juice, buttermilk, or sour cream in a batter, bubbles of carbon dioxide gas are formed from decomposition of the resulting carbonic acid, and the batter rises. Baking powder is a combination of sodium bicarbonate and one or more acid salts that react when the two chemicals come in contact with water in the batter. Many people like to put lemon juice or vinegar, both of which are acids, on cooked fish, figure 4.8. It turns out that fish have volatile amines, bases, in their systems, which are neutralized by the acids to yield involatile ammonium salts. This reduces the odor of the fish and also adds a sour taste that we seem to enjoy. An image is shown of two fish with heads removed and skin on, with lemon slices placed in the body cavity. The first line of an equation below the image reads CH subscript 3 COOH plus NH subscript 2 CH subscript 2 CH subscript 2 CH subscript 2 NH subscript 2 arrow CH subscript 2 arrow CH subscript negative sign plus NH subscript 3 superscript positive sign CH subscript 2 CH subscript 2 CH subscript 2 CH subscript 2 Na. The second line of the equation reads acetic acid plus sign putrescine arrow acetate ion plus sign putracinium ion. Figure 4.8. A neutralization reaction takes place between citric acid in lemons or acetic acid in vinegar and the bases in the flesh of fish. Pickling is a method used to preserve vegetables using a naturally produced acidic environment. The vegetable, such as a cucumber, is placed in a sealed jar submerged in a brine solution. The brine solution favors the growth of beneficial bacteria and suppresses the growth of harmful bacteria. The beneficial bacteria feed on starches in the cucumber and produce lactic acid as a waste product in a process called fermentation. The lactic acid eventually increases the acidity of the brine to a level that kills any harmful bacteria, which require a basic environment. Without the harmful bacteria consuming the cucumbers, they are able to last much longer than if they were unprotected. A byproduct of the pickling process changes the flavor of the vegetables, with the acid making them taste sour. Link to learning. Explore the microscopic view of strong and weak acids and bases. Oxidation-reduction reactions. Earth's atmosphere contains about 20% molecular oxygen, O2, a chemically reactive gas that plays an essential role in the metabolism of aerobic organisms and in many environmental processes that shape the world. The term oxidation was originally used to describe chemical reactions involving O2, but its meaning has evolved to refer to a broad and important reaction class known as oxidation-reduction, redox, reactions. A few examples of such reactions will be used to develop a clear picture of this classification. Some redox reactions involve the transfer of electrons between reactant entities to yield ionic products, such as the reaction between sodium and chlorine to yield sodium chloride. 2NaS plus Cl2G2NaCls. It is helpful to view the process with regard to each individual reactant, that is, to represent the fate of each reactant in the form of an equation called a half reaction. 2NaS to resorm of an equation called a half reaction. These equations show that Na atoms lose electrons while Cl atoms, and for redox reactions of this sort, the loss and gain of electrons define the complementary processes that occur. Oxidation reduction equals loss of electrons, gain of electrons. In this reaction, then, sodium is oxidized and chlorine undergoes reduction. Viewed from a more active perspective, sodium functions as a reducing agent, reductant, since it provides electrons to, or reduces, chlorine. Likewise, chlorine functions as an oxidizing agent, oxidant, as it effectively removes electrons from oxidizes sodium. Reducing agent oxidizing agent equals species that is oxidized species that is reduced. Some redox processes, however, do not involve the transfer of electrons. Consider, for example, a reaction similar to the one yielding sodium chloride. H2G plus Cl2G2 HCl of G. The product of this reaction is a covalent compound, so transfer of electrons in the explicit sense is not involved. To clarify the similarity of this reaction to the previous one and permit an unambiguous definition of redox reactions, a property called oxidation number has been defined. The oxidation number, or oxidation state, of an element in a compound is the charge its atoms would possess if the compound were ionic. The following guidelines are used to assign oxidation numbers to each element in a molecule or ion. The oxidation number of an atom in an elemental substance is 0. The oxidation number of a monatomic ion is equal to the ion's charge. Oxidation numbers for common nonmetals are usually assigned as follows. Hydrogen, +1 when combined with nonmetals, -1 when combined with metals. Oxygen, -2 in most compounds, sometimes -1, so-called peroxides O22-, very rarely -12, so-called superoxides O2-. Positive values when combined with F values vary. Halogens -1 for F always, -1 for other halogens except when combined with oxygen or other halogens. The sum of oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge on the molecule or ion. Note, the proper convention for reporting charge is to write the number first, followed by the sign e.g. 2+, while oxidation number is written with the reversed sequence, sign followed by number e.g. +2. This convention aims to emphasize the distinction between these two related properties. Example 4.5. Assigning oxidation numbers. Follow the guidelines in this section of the text to assign oxidation numbers to all the elements in the following species: A. H2S, B. SO32-, C. Na2SO4. Solution: A. According to Guideline 3, the oxidation number for H is +1. Using this oxidation number and the compound's formula, Guideline the fourth of may then be used to calculate the oxidation number for sulfur. Charge ONH2S equals 0 equals 2 times +1, plus 1 times X, X equals 0 minus 2 times +1 equals -2. B. Guideline 3 suggests the oxidation number for oxygen is -2. Using this oxidation number and the ion's formula, Guideline the fourth of may then be used to calculate the oxidation number for sulfur. Charge OnSO32- equals -2 equals 3 times -2 plus 1 times X equals -2 minus 3 times -2 equals +4. C. For ionic compounds, it's convenient to According to Guideline 2, the oxidation number for sodium is +1. Assuming the usual oxidation number for oxygen, -2 per Guideline 3, the oxidation number for sulfur is calculated as directed by Guideline 4. Charge OnSO42- equals -2 equals 4 times -2 plus 1 times X equals -2 minus 4 times -2 equals +6. Check your learning. Assign oxidation ALH3, CnH4 plus, DH2PO4 minus. Answer: AN plus 5, B, Al plus 3, CN minus 3, D, P plus 5. Using the oxidation number concept, an all-inclusive definition of redox reaction has been established. Oxidation reduction, redox reactions, are those in which one or more elements involved undergo a change in oxidation number. While the vast majority of redox reactions involve changes in oxidation number for 2 or more elements, a few interesting exceptions to this rule do exist. Example 4.6. Definitions for the complementary processes of this reaction class are correspondingly revised as shown here. Oxidation reduction equals increase in oxidation number, decrease in oxidation number. Returning to the reactions used to introduce this topic, they may now both be identified as redox processes. In the reaction between sodium and chlorine to yield sodium chloride, sodium is oxidized. Its oxidation number increases from 0 in Na to +1 in sodium chloride, and chlorine is reduced. Its oxidation number decreases from 0 in Cl2 to -1 in sodium chloride. In the reaction between molecular hydrogen and chlorine, hydrogen is oxidized. Its oxidation number increases from 0 in H2 to +1 in HCl, and chlorine is reduced. Its oxidation number decreases from 0 in Cl2 to -1 in HCl. Several subclasses of redox reactions are recognized, including combustion reactions in which the reductant, also called a fuel, and oxidant, often but not necessarily molecular oxygen, react vigorously and produce significant amounts of heat, and often light, in the form of a flame. Solid rocket fuel reactions, such as the one depicted in Figure 4.1, are combustion processes. A typical propellant reaction in which solid aluminum is oxidized by ammonium perchlorate is represented by this equation. 10 Als plus 6 New Hampshire 4ClO4 S 4 aluminium oxide S plus 2 AlCl3S plus 12H2OG plus 3N2G. Link to learning. Watch a brief video showing the test firing of a small-scale, prototype, hybrid rocket engine planned for use in the new Space Launch System being developed by NASA. The first engines firing at 3S, green flame, use a liquid fuel/oxidant mixture, and the second, more powerful engines firing at 4S, yellow flame, use a solid mixture. Single displacement replacement reactions are redox reactions in which an ion in solution is displaced or replaced via the oxidation of a metallic element. One common example of this type of reaction is the acid oxidation of certain metals. ZNs plus 2HClAq, ZnCl2aq plus H2G. Metallic elements may also be oxidized by solutions of other metal salts. For example, Cus plus 2 silver 1 nitrate Aq, copper 1 nitrate 2 Aq plus 2 Ags. This reaction may be observed by placing copper wire in a solution containing silver. Ions in solution are reduced to elemental silver at the surface of the copper wire, and the resulting Cu2 plus ions dissolve in the solution to yield a characteristic blue color, figure 4.9. This figure contains 3 photographs. In A coiled copper wire is shown beside a test tube filled with a clear, colorless liquid. In B, the wire has been inserted into the test tube with the clear, colorless liquid. In C, the test tube contains a light blue liquid, and the coiled wire appears to have a fuzzy silver-gray coating. Figure 4.9a. A copper wire is shown next to a solution containing silver ions. B. Displacement of dissolved silver ions by copper ions results in C. Accumulation of gray-colored silver metal on the wire and development of a blue color in the solution due to dissolved copper ions. Credit: modification of work by Mark Ott. Example 4.6. Describing redox reactions. Identify which equations represent redox reactions, providing a name for the reaction if appropriate. For those reactions identified as redox, name the oxidant and reductant. A. Zinc carbonate SZNOs plus CO2G. B2GAl plus 3. Bridge 2L2 Gabber 3. S. Decarbonate DC2 hydrogen oxide AQ 2H2OL plus K2SO4 AQ barium sulfates S plus 2 KClAq. EC2H4G plus 3O2G2 CO2G plus 2H2OL. Solution. Redox reactions are identified. A. This is not a redox reaction since oxidation numbers remain unchanged for all elements. B. This is a redox reaction. Gallium is oxidized, its oxidation number increasing from 0 in GAl to plus 3 in GaBr3s. The reducing agent is GAl. Bromine is reduced, its oxidation number decreasing from 0 in bridge 2L to -1 in GaBr3s. The oxidizing agent is bridge 2L. C. This is a redox reaction. It is a particularly interesting process as it involves the same element, oxygen, undergoing both oxidation and reduction, a so-called disproportionation reaction. Oxygen is oxidized, its oxidation number increasing from -1 in H2O2aq to 0 in O2g. Oxygen is also reduced, its oxidation number decreasing from -1 in H2O2aq to -2 in H2OL. For disproportionation reactions, the same substance functions as an oxidant and a reductant. D. This is not a redox reaction, since oxidation numbers remain unchanged for all elements. E. This is a redox reaction, combustion. Carbon is oxidized, its oxidation number increasing from -2 in C2H4G to +4 in CO2G. The reducing agent, fuel, is C2H4G. Oxygen is reduced, its oxidation number decreasing from 0 in O2G to -2 in H2OL. The oxidizing agent is O2G. Check your learning. This equation describes the production of tin 2 chloride, SNs plus 2 HClG, SnCl2s plus H2G. Is this a redox reaction? If so, provide a more specific name for the reaction if appropriate, and identify the oxidant and reductant. Answer: yes, a single replacement reaction. SNS is the reductant, HCl is the oxidant. Balancing redox reactions via the half-reaction method. Redox reactions that take place in aqueous media often involve water, hydronium ions, and hydroxide ions as reactants or products. Although these species are not oxidized or reduced, they do participate in chemical change in other ways, e.g., by providing the elements required to form oxyanions. Equations representing these reactions are sometimes very difficult to balance by inspection, so systematic approaches have been developed to assist in the process. One very useful approach is to use the method of half reactions, which involves the following steps. 1. Write the two half reactions representing the redox process. 2. Balance all elements except oxygen and hydrogen. 3. Balance oxygen atoms by adding H2O molecules. 4. Balance hydrogen atoms by adding H+ ions. 5. Balance charge by adding electrons. 6. If necessary, multiply each half reaction's coefficients by the smallest possible integers to yield equal numbers of electrons in each. 7. Add the balanced half reactions together and simplify by removing species that appear on both sides of the equation. 8. For reactions occurring in basic media, excess hydroxide ions, carry out these additional steps. Add OH- ions to both sides of the equation in numbers equal to the number of H+ ions. On the side of the equation containing both H+ and OH- ions, combine these ions to yield water molecules. Simplify the equation by removing any redundant water molecules. 9. Finally, check to see that both the number of atoms and the total charges 1 are balanced. Example 4.7. Balancing redox reactions in acidic solution. Write a balanced equation for the reaction between dichromate ion and iron 2 to yield iron 3 and chromium 3 in acidic solution. Cr2O72 minus plus Fe2 plus Cr3 plus Fe3 plus. Solution. Step 1. Write the two half reactions. Each half reaction will contain one reactant and one product with one element in common. Fe2 plus Fe3 plus. Cr2O72 minus Cr3 plus. Step 2. Balance all elements except oxygen and hydrogen. The iron half reaction is already balanced, but the chromium half reaction shows two crossing atoms on the left and one crossing atom on the right. Changing the coefficient on the right side of the equation to 2 achieves balance with regard to crossing atoms. Fe2 plus Fe3 plus. Cr2O72 minus 2 Cr3 plus. Step 3. Balance oxygen atoms by adding H2O molecules. The iron half reaction does not contain O atoms. The chromium half reaction shows 7 O atoms on the left and none on the right, so 7 water molecules are added to the right side. Fe2 plus Fe3 plus Cr2O, 7 2 minus 2 Cr3 plus 7 H2O. Step 4. Balance hydrogen atoms by adding H+ ions. The iron half reaction does not contain H atoms. The chromium half reaction shows 14 H atoms on the right and none on the left, so 14 hydrogen ions are added to the left side. Fe2 plus Fe3 plus Cr2O 72 minus plus 14H plus 2 Cr3 plus 7H2O. Step 5. Balance charge by adding electrons. The iron half reaction shows a total charge of 2 plus on the left side, 1 Fe2 plus ion, and 3 plus on the right side, 1 Fe3 plus ion. Adding 1 electron to the right side brings that side's total charge to 3 plus plus 1 minus equals 2 plus, and charge balance is achieved. The chromium half reaction shows a total charge of 1 times 2 minus plus 14 times 1 plus equals 12 plus on the left side, 1 Cr2O 7 2- ion, and 14 H plus ions. The total charge on the right side is 2 times 3 plus equals 6 plus 2 Cr3 plus ions. Adding 6 electrons to the left side will bring that side's total charge to 12 plus 6 minus equals 6 plus, and charge balance is achieved. Fe2 plus Fe3 plus E minus Cr2O 7 2- plus 14 H plus 6 E minus 2 Cr3 plus 7 H 2O. Step 6. Multiply the two half reactions so the number of electrons in one reaction equals the number of electrons in the other reaction. To be consistent with mass conservation and the idea that redox reactions involve the transfer, not creation or destruction, of electrons, the iron half reaction's coefficient must be multiplied by 6. 6 Fe2 plus 6 Fe3 plus 6 E minus Cr2O 7 2- plus 6 E minus plus 1 4H plus 2 Cr3 plus 7 H2O. Step 7. Add the balanced half reactions and cancel species that appear on both sides of the equation. 6 Fe2 plus Cr2O 7 2- plus 6 E minus plus 1 4H plus 6 Fe3 plus 6 E minus plus 2 Cr3 plus 7 H2O. Only the 6 electrons are redundant species. Removing them from each side of the equation yields the simplified, balanced equation here. 6 Fe2 plus Cr2O 7 2- plus 14H plus 6 Fe3 plus 2 Cr3 plus 7 H2O. A final check of atom and charge balance confirms the equation is balanced. Reactants products: Fe66, Cr22, O77, H1414. Charge 24 plus 24 plus. Check your learning. In basic solution, molecular chlorine, Cl2, reacts with hydroxide ions, OH-, to yield chloride ions, Cl-, and chlorate ions, ClO3-. Hint: this is a disproportionation reaction in which the element chlorine is both oxidized and reduced. Write a balanced equation for this reaction. Answer: 3Cl2, Aq, plus 6OH- Aq, 5Cl- Aq, plus ClO3- Aq, plus 3H2OL. Learning objectives. By the end of this section, you will be able to explain the concept of stoichiometry as it pertains to chemical reactions. Use balanced chemical equations to derive stoichiometric factors relating amounts of reactants and products. Perform stoichiometric calculations involving mass, moles, and solution molarity. A balanced chemical equation provides a great deal of information in a very succinct format. Chemical formulas provide the identities of the reactants and products involved in the chemical change, allowing classification of the reaction. Coefficients provide the relative numbers of these chemical species, allowing a quantitative assessment of the relationships between the amounts of substances consumed and produced by the reaction. These quantitative relationships are known as the reaction's stoichiometry, a term derived from the Greek words stoichion, meaning element, and metron, meaning measure. In this module, the use of balanced chemical equations for various stoichiometric applications is explored. The general approach to using stoichiometric relationships is similar in concept to the way people go about many common activities. Food preparation, for example, offers an appropriate comparison. A recipe for making 8 pancakes calls for 1 cup pancake mix, 34 cup milk, and 1 egg. The equation representing the preparation of pancakes per this recipe is 1 cup mix plus 3/4 cup milk plus 1 egg, 8 pancakes. If 2 dozen pancakes are needed for a big family breakfast, the ingredient amounts must be increased proportionally according to the amounts given in the recipe. For example, the number of eggs required to make 24 pancakes is 24 pancakes times 1 egg, 8 pancakes equals 3 eggs. Balanced chemical equations are used in much the same fashion to determine the amount of one reactant required to react with a given amount of another reactant, or to yield a given amount of product, and so forth. The coefficients in the balanced equation are used to derive stoichiometric factors that permit computation of the desired quantity. To illustrate this idea, consider the production of ammonia by reaction of hydrogen and nitrogen, N2G plus 3H2G, 2NH3G. This equation shows ammonia molecules are produced from hydrogen molecules in a 2:3 ratio, and stoichiometric factors may be derived using any amount number unit. 2NH3 molecules 3H to compute the number of ammonia molecules produced from a given number of hydrogen molecules, or the number of hydrogen molecules required to produce a given. Similar factors may be derived for any pair of substances in any chemical equation. Example 4.8. Moles of reactant required in a reaction. How many moles of I2 are required to react with 0.429 moles of Al according to the following equation? See Figure 4.10. 2 Al plus 3 I2 2 Ali3. This figure shows 3 photos with an arrow leading from one to the next. The first photo shows a small pile of iodine and aluminum on a white surface. The second photo shows a small amount of purple smoke coming from the pile. The third photo shows a large amount of purple and gray smoke coming from the pile. Figure 4.10. Aluminum and iodine react to produce aluminum iodide. The heat of the reaction vaporizes some of the solid iodine as a purple vapor. Credit: Modification of work by Mark Ott. Solution: referring to the balanced chemical equation, the stoichiometric factor relating the two substances of interest is 3 mol I, 22 moles Al. The molar amount of iodine is derived by multiplying the provided molar amount of aluminum by this factor. This figure shows 2 pink rectangles. The first is labeled moles of Al. This rectangle is followed by an arrow pointing right to a second rectangle labeled moles of I subscript 2. Mol I2 equals 0.429 moles Al times 3 mol I 22 moles. L equals 0.644 mol I2. Check your learning. How many moles of calcium hydroxide are required to react with 1.36 moles of H3PO4 to produce calcium phosphate according to the equation 3 calcium hydroxide plus 2 hydrogen phosphate, calcium phosphate plus 6H2O? Answer: 2.04 moles. Example 4.9. Number of product molecules generated by a reaction. How many carbon dioxide molecules are produced when 0.75 moles of propane is combusted according to this equation? C3H8 plus 5O2 3 CO2 plus 4H2O. Solution: the approach here is the same as for example 4.8, though the absolute number of molecules is requested, not the number of moles of molecules. This will simply require use of the moles to numbers conversion factor, Avogadro's number. The balanced equation shows that carbon dioxide is produced from propane in a 3:1 ratio. 3 mol CO, 21 mol C3H8. Using this stoichiometric factor, the provided molar amount of propane and Avogadro's number, this figure shows 2 pink rectangles. The first is labeled moles of C subscript 3H subscript 8. This rectangle is followed by an arrow pointing right to a second rectangle labeled moles of CO subscript 2. 0.75 moles C3H8 times 3 mol CO, 21 mol C3H8 times 6.022 times 1023 CO2 molecules. CO2 equals 1.4 times 1024 CO2 molecules. Check your learning. How many NH3 molecules are produced by the reaction of 4.0 moles of calcium hydroxide according to the following equation? Answer: these examples directly measuring numbers of atoms and molecules is, however, not an easy task, and the practical application of stoichiometry requires that we use the more readily measured property of mass. Example 4.10. Relating masses of reactants and products. What mass of sodium hydroxide, NaOH, would be required to produce 16 grams of the antacid milk of magnesia, magnesium hydroxide 2, by the following reaction? MgCl2aq plus 2NaOH magnesium hydroxide 2S plus 2 sodium chloride Aq. Solution. The approach used previously in example 4.8 and example 4.9 is likewise used here. That is, we must derive an appropriate stoichiometric factor from the balanced chemical equation and use it to relate the amounts of the two substances of interest. In this case, however, masses, not molar amounts, are provided and requested, so additional steps of the sort learned in the previous chapter are required. The calculations required are outlined in this flowchart. This figure shows 4 rectangles. The first is shaded yellow and is labeled mass of Mg, OH, subscript 2. This rectangle is followed by an arrow pointing right to a second rectangle, which is shaded pink and is labeled moles of Mg, OH, subscript 2. This rectangle is followed by an arrow pointing right to a third rectangle, which is shaded pink and is labeled moles of NaOH. This rectangle is followed by an arrow pointing right to a fourth rectangle, which is shaded yellow and is labeled mass of NaOH. 16 grams magnesium hydroxide times 1 mole magnesium hydroxide, 0.3 grams magnesium hydroxide times 2 moles NaOH. 1 mole magnesium hydroxide times 40.0 grams NaOmol NaOH equals 22 grams NaOH. Check your learning. What mass of gallium oxide, gallium-3 oxide can be prepared from 29? The equation for the reaction is 4Ga plus 3O22 gallium-3 oxide. Answer: 39.0 grams. Example 4.11. Relating masses of reactants. What mass of oxygen gas, O2, from the air is consumed in the combustion of 702 grams of octane, C8H18, one of the principal components of gasoline? 2C8H18 plus 250, 216, CO2 plus 18H2O. Solution. The approach required here is the same as for the example 4.10, differing only in that the provided and requested masses are both for reactant species. This figure shows 4 rectangles. The first is shaded yellow and is labeled mass of C subscript 8H subscript 18. This rectangle is followed by an arrow pointing right to a second rectangle, which is shaded pink and is labeled moles of C subscript 8H subscript 18. This rectangle is followed by an arrow pointing right to a third rectangle, which is shaded pink and is labeled moles of O subscript 2. This rectangle is followed by an arrow pointing right to a fourth rectangle, which is shaded yellow and is labeled mass of O subscript 2. 702 GC8H18 times 1 mol C 8H1811 4.2 3GC8H18 times 25 molo 22 mol C 8H18 times 32.00 go 2 molo 2 equals 2.4 6 times 103 go 2. Check your learning. What mass of CO is required to react with 25.13 grams of iron 3 oxide according to the equation iron 3 oxide plus 3CO2? Answer: 13.22 grams. These examples illustrate just a few instances of reaction stoichiometry calculations. Numerous variations on the beginning and ending computational steps are possible depending upon what particular quantities are provided and sought, volumes, solution concentrations, and so forth. Regardless of the details, all these calculations share a common essential component: the use of stoichiometric factors derived from balanced chemical equations. Figure 4.11 provides a general outline of the various computational steps associated with many reaction stoichiometry calculations. This flowchart shows 10 rectangles connected by double-headed arrows. To the upper left, a rectangle is shaded lavender and is labeled volume of pure substance A. This rectangle is followed by a horizontal double-headed arrow labeled density. It connects to a second rectangle which is shaded yellow and is labeled mass of A. This rectangle is followed by a double-headed arrow which is labeled molar mass that connects to a third rectangle which is shaded pink and is labeled moles of A. To the left of this rectangle is a horizontal double-headed arrow labeled molarity, which connects to a lavender rectangle which is labeled volume of solution A. The pink moles of A rectangle is also connected with a double-headed arrow below and to the left. This arrow is labeled Avogadro's number. It connects to a green shaded rectangle that is labeled number of particles of A. To the right of the pink moles of A, rectangle is a horizontal double-headed arrow which is labeled stoichiometric factor. It connects to a second pink rectangle which is labeled moles of B. A double-headed arrow which is labeled molar mass extends from the top of this rectangle above and to the right to a yellow shaded rectangle labeled mass of B. A horizontal double-headed arrow which is labeled density links to a lavender rectangle labeled volume of substance B, quote, to the right. A horizontal double-headed arrow labeled molarity extends right to the pink moles of B rectangle. This arrow connects to a lavender rectangle that is labeled volume of substance B. Another double-headed arrow extends below and to the right of the pink moles of B rectangle. This arrow is labeled Avogadro's number, and it extends to a green rectangle which is labeled number of particles of B. Figure 4.11. The flowchart depicts the various computational steps involved in most reaction stoichiometry calculations. Chemistry in everyday life. Airbags. Airbags, figure 4.12, are a safety feature provided in most automobiles since the 1990s. The effective operation of an airbag requires that it be rapidly inflated with an appropriate volume of gas when the vehicle is involved in a collision. This requirement is satisfied in many automotive airbag systems through use of explosive chemical reactions, one common choice being the decomposition of sodium azide, NaN3. When sensors in the vehicle detect a collision, an electrical current is passed through a carefully measured amount of NaN3 to initiate its decomposition. 2NaN3 S3N2G plus 2 NaS. This reaction is very rapid, generating gaseous nitrogen that can deploy and fully inflate a typical airbag in a fraction of a second, approximately 0.03 to 0.1 s. Among many engineering considerations, the amount of sodium azide used must be appropriate for generating enough nitrogen gas to fully inflate the airbag and ensure its proper function. For example, a small mass, approximately 100 g of NaN3, will generate approximately 50 L of N2. This photograph shows the inside of an automobile from the driver's side area. The image shows inflated airbags positioned just in front of the driver's and passenger's seats and along the length of the passenger side over the windows. A large, round airbag covers the steering wheel. Figure 4.12 airbags deploy upon impact to minimize serious injuries to passengers. Credit: John Seidman. Learning objectives. By the end of this section, you will be able to explain the concepts of theoretical yield and limiting reactants/reagents. Derive the theoretical yield for a reaction under specified conditions. Calculate the percent yield for a reaction. The relative amounts of reactants and products represented in a balanced chemical equation are often referred to as stoichiometric amounts. All the exercises of the preceding module involve stoichiometric amounts of reactants. For example, when calculating the amount of product generated from a given amount of reactant, it was assumed that any other reactants required were available in stoichiometric amounts or greater. In this module, more realistic situations are considered, in which reactants are not present in stoichiometric amounts. Limiting reactant. Consider another food analogy, making grilled cheese sandwiches, figure 4.13. 1 slice of cheese plus 2 slices of bread, 1 sandwich. Stoichiometric amounts of sandwich ingredients for this recipe are bread and cheese slices in a 2-to-1 ratio. Provided with 28 slices of bread and 11 slices of cheese, one may prepare 11 sandwiches per the provided recipe, using all the provided cheese and having 6 slices of bread left over. In this scenario, the number of sandwiches prepared has been limited by the number of cheese slices, and the bread slices have been provided in excess. This figure has 3 rows showing the ingredients needed to make a sandwich. The first row reads, 1 sandwich equals 2 slices of bread plus 1 slice of cheese. 2 slices of bread and 1 slice of cheese are shown. The second row reads, provided with 28 slices of bread plus 11 slices of cheese. There are 28 slices of bread and 11 slices of cheese shown. The third row reads, we can make 11 sandwiches plus 6 slices of bread left over. 11 sandwiches are shown with 6 extra slices of bread. Figure 4.13 sandwich making can illustrate the concepts of limiting and excess reactants. Consider this concept now with regard to a chemical process, the reaction of hydrogen with chlorine to yield hydrogen chloride, H2G plus Cl2G to HCl of G. The balanced equation shows the hydrogen and chlorine react in a 1-to-1 stoichiometric ratio. If these reactants are provided in any other amounts, one of the reactants will nearly always be entirely consumed, thus limiting the amount of product that may be generated. This substance is the limiting reactant, and the other substance is the excess reactant. Identifying the limiting and excess reactants for a given situation requires computing the molar amounts of each reactant provided and comparing them to the stoichiometric amounts represented in the balanced chemical equation. For example, imagine combining 3 moles of H2 and 2 moles of Cl2. This represents a 3-to-2, or 1.51, ratio of hydrogen to chlorine present for reaction, which is greater than the stoichiometric ratio of 1-to-1. Hydrogen, therefore, is present in excess, and chlorine is the limiting reactant. Reaction of all the provided chlorine, 2 moles, will consume 2 moles of the 3 moles of hydrogen provided, leaving 1 mole of hydrogen unreacted. An alternative approach to identifying the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. Each reactant amount is used to separately calculate the amount of product that would be formed per the reaction stoichiometry. The reactant yielding the lesser amount of product is the limiting reactant. For the example in the previous paragraph, complete reaction of the hydrogen would yield mole HCl produced equals 3 mole H2 times 2 moles, HCl1 mole H2 equals 6 moles HCl. Complete reaction of the provided chlorine would produce mole HCl produced equals 2 mole Cl 2 times 2 moles HCl1 mole Cl2 equals 4 moles HCl. The chlorine will be completely consumed once 4 moles of HCl have been produced. Since enough hydrogen was provided to yield 6 moles of HCl, there will be unreacted hydrogen remaining once this reaction is complete. Chlorine, therefore, is the limiting reactant, and hydrogen is the excess reactant. Figure 4.14. The figure shows a space-filling molecular models reacting. There is a reaction arrow pointing to the right in the middle. To the left of the reaction arrow, there are 3 molecules, each consisting of 2 green spheres bonded together. There are also 5 molecules, each consisting of 2 smaller white spheres bonded together. Above these molecules is the label before reaction, and below these molecules is the label 6H subscript 2 and 4Cl subscript 2. To the right of the reaction arrow, there are 8 molecules, each consisting of 1 green sphere bonded to a smaller white sphere. There are also 2 molecules, each consisting of 2 white spheres bonded together. Above these molecules is the label after reaction, and below these molecules is the label 8HCl and 2H subscript 2. Figure 4.14. When H2 and Cl2 are combined in non-stoichiometric amounts, one of these reactants will limit the amount of HCl that can be produced. This illustration shows a reaction in which hydrogen is present in excess and chlorine is the limiting reactant. Link to learning. View this interactive simulation illustrating the concepts of limiting and excess reactants. Example 4.12. Identifying the limiting reactant. Silicon nitride is a very hard, high-temperature resistant ceramic used as a component of turbine blades in jet engines. It is prepared according to the following equation. 3Cis plus 2N2G silicon nitride 4S. Which is the limiting reactant when 2.00 grams of Si and 1.50 grams of N2 react? Solution. Compute the provided molar amounts of reactants, and then compare these amounts to the balanced equation to identify the limiting reactant. Mole Si equals 2.00 grams Si times 1 mole Si, 28.09 grams, Si equals 0.0712 molesation. Mole N2 equals 1.50 GN2 times 1 mole N228.02 Tilde GN2 equals 0.0535 mole N2. The stoichiometric SiN2 ratio is 3 moles Si is provided in a less than stoichiometric amount, and so is the limiting reactant. Alternatively, compute the amount of product expected for complete reaction of each of the provided reactants. The 0.0712 moles of silicon would yield mol psi 3n4 produced equals 0.0712 moles, psi times 1 mol psi 3n4, 3 mol psi equals 0.0237 mol psi 3n4, while the 0.0535 moles of nitrogen would produce mol psi 3n4 produced equals 0.0535 mol N2 times 1 mol psi 3n4, 2 equals 0.0268 mol psi 3n4. Since silicon yields the lesser, check your learning. Which is the limiting reactant when 5.00 grams of H2 and 10.0 grams of O2 react and form water? Answer: O2. Percent yield. The amount of product that may be produced by a reaction under specified conditions, as calculated per the stoichiometry of an appropriate balanced chemical equation, is called the theoretical yield of the reaction. In practice, the amount of product obtained is called the actual yield, and it is often less than the theoretical yield for a number of reasons. Some reactions are inherently inefficient, being accompanied by side reactions that generate other products. Others are, by nature, incomplete. Consider the partial reactions of weak acids and bases discussed earlier in this chapter. Some products are difficult to collect without some loss, and so less than perfect recovery will reduce the actual yield. The extent to which a reaction's theoretical yield is achieved is commonly expressed as its percent yield. Percent yield equals actual yield theoretical yield times 100%. Actual and theoretical yields may be expressed as masses or molar amounts or any other appropriate property, e.g. volume if the product is a gas. As long as both yields are expressed using the same units, these units will cancel when percent yield is calculated. Example 4.13. Calculation of percent yield. Upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams copper metal was obtained according to the equation. QSO4 AQ plus ZNs Kes plus zinc sulfate AQ. What is the percent yield? Solution. The provided information identifies copper sulfate as the limiting reactant, and so the theoretical yield is found by the approach illustrated in the previous module as shown here. 1.274 GCuSO 4 times 1 mol QSO, 4159.62 GCuSO 4 times 1 mol Cu1 mol QSO 4 times 63.55 grams Cu1 mol Cu equals 0.5072 grams Cu. Miss. See, using this theoretical yield and the provided value for actual yield, the percent yield is calculated to be percent yield equals actual yield theoretical yield times 100% yield equals 0.392 grams Cu 0.5072 grams Cu times 100 equals 77.3%. Check your learning. What is the percent yield of a reaction that produces 12.5 grams of the gas Freon CF2Cl2 from 32.9 grams of CCl4 and excess HF? CCl4 plus 2HFCF2Cl2 plus 2HCl. Answer: 48.3%. How sciences interconnect. Green chemistry and atom economy. The purposeful design of chemical products and processes that minimize the use of environmentally hazardous substances and the generation of waste is known as green chemistry. Green chemistry is a philosophical approach that is being applied to many areas of science and technology, and its practice is summarized by guidelines known as the 12 Principles of Green Chemistry. See details at this website. One of the 12 principles is aimed specifically at maximizing the efficiency of processes for synthesizing chemical products. The atom economy of a process is a measure of this efficiency, defined as the percentage by mass of the final product of a synthesis relative to the masses of all the reactants used. Atom economy equals mass of product mass of reactants times 100%. Though the definition of atom economy at first glance appears very similar to that for percent yield, be aware that this property represents a difference in the theoretical efficiencies of different chemical processes. The percent yield of a given chemical process, on the other hand, evaluates the efficiency of a process by comparing the yield of product actually obtained to the maximum yield predicted by stoichiometry. The synthesis of the common non-prescription pain medication, ibuprofen, nicely illustrates the success of a green chemistry approach, figure 4.15. First marketed in the early 1960s, ibuprofen was produced using a 6-step synthesis that required 514 grams of reactants to generate each mole, 206 grams, of ibuprofen, an atom economy of 40%. In the 1990s, an alternative process was developed by the BHC company, now BASF Corporation, that requires only 3 steps and has an atom economy of approximately 80%, nearly twice that of the original process. The BHC process generates significantly less chemical waste, uses less hazardous and recyclable materials, and provides significant cost savings to the manufacturer and, subsequently, the consumer. In recognition of the positive environmental impact of the BHC process, the company received the Environmental Protection Agency's Greener Synthetic Pathways Award in 1997. This figure is labeled A and B. Part A shows an open bottle of ibuprofen and a small pile of ibuprofen tablets beside it. Part B shows a reaction along with line structures. The first line structure looks like a diagonal line pointing down and to the right, then up and to the right, and then down and to the right. At this point, it connects to a hexagon with alternating double bonds. At the first trough, there is a line that points straight down. From this structure, there is an arrow pointing downward. The arrow is labeled HF on the left and CH subscript 3 CO subscript 2O quelt on the right. The next line structure looks exactly like the first line structure, but it has a line angled down and to the right from the lower right point of the hexagon. This line is connected to another line which points straight down. Where these two lines meet, there is a double bond to an O atom. There is another arrow pointing downward, and it is labeled H subscript 2 Rainy and I. The next structure looks very similar to the second, previous structure, except in place of the double bonded O, there is a singly bonded OH group. There is a final reaction arrow pointing downward, and it is labeled COPD. The final structure is similar to the third, previous structure, except in place of the OH group, there is another line that points down and to the right to an OH group. At these two lines, there is a double bonded O. Figure 4.15a ibuprofen is a popular non-prescription pain medication commonly sold as 200 milligrams tablets. B. The BHC process for synthesizing ibuprofen requires only 3 steps and exhibits an impressive atom economy. Credit A, modification of work by Derek Coetzee, learning objectives. By the end of this section, you will be able to describe the fundamental aspects of titrations and gravimetric analysis. Perform stoichiometric calculations using typical titration and gravimetric data. In the 18th century, the strength, actually the concentration, of vinegar samples was determined by noting the amount of potassium carbonate, K2CO3, which had to be added, a little at a time, before bubbling ceased. The greater the weight of potassium carbonate added to reach the point where the bubbling ended, the more concentrated the vinegar. We now know that the effervescence that occurred during this process was due to reaction with acetic acid, CH3CO2H, the compound primarily responsible for the odor and taste of vinegar. Acetic acid reacts with potassium carbonate according to the following equation: 2CH3 Colorado 2 HAQ plus K 2CO3S 2CH3 Colorado 2 KAQ plus CO2G plus H2OL. The bubbling was due to the production of CO2. The test of vinegar with potassium carbonate is one type of quantitative analysis, the determination of the amount or concentration of a substance in a sample. In the analysis of vinegar, the concentration of the solute, acetic acid, was determined from the amount of reactant that combined with the solute present in a known volume of the solution. In other types of chemical analyses, the amount of a substance present in a sample is determined by measuring the amount of product that results. Titration. The described approach to measuring vinegar strength was an early version of the analytical technique known as titration analysis. A typical titration analysis involves the use of a burette, figure 4.16, to make incremental additions of a solution containing a known concentration of some substance, the titrant, to a sample solution containing the substance whose concentration is to be measured, the analyte. The titrant and analyte undergo a chemical reaction of known stoichiometry, and so measuring the volume of titrant solution required for complete reaction with the analyte, the equivalence point of the titration, allows calculation of the analyte concentration. The equivalence point of a titration may be detected visually if a distinct change in the appearance of the sample solution accompanies the completion of the reaction. The halt of bubble formation in the classic vinegar analysis is one such example, though, more commonly, special dyes called indicators are added to the sample solutions to impart a change in color at or very near the equivalence point of the titration. Equivalence points may also be detected by measuring some solution property that changes in a predictable way during the course of the titration. Regardless of the approach taken to detect a titration's equivalence point, the volume of titrant actually measured is called the endpoint. Properly designed titration methods typically ensure that the difference between the equivalence and endpoints is negligible. Though any type of chemical reaction may serve as the basis for a titration analysis, the three described in this chapter, precipitation, acid-base, and redox, are most common. Additional details regarding titration analysis are provided in the chapter on acid-base equilibria. Two pictures are shown. A person is shown pouring a liquid from a small beaker into a burette. The person is wearing goggles and gloves as she transfers the solution into the burette. In B, a close-up view of the markings on the side of the burette is shown. The markings for 10, 15, and 20 are clearly shown with horizontal rings printed on the burette. Between each of these whole number markings, half markings are also clearly shown with horizontal line segment markings. Figure 4.16a, a student fills a burette in preparation for a titration analysis. B, a typical burette permits volume measurements to the nearest 0.01 milliliters. Credit A, modification of work by Mark Blazer and Matt Evans. Credit B, modification of work by Mark Blazer and Matt Evans. Example 4.14. Titration analysis. The endpoint in a titration of a 50.00 ml sample of aqueous HCl was reached by addition of 35.23 milliliters of 0.250 MnAOH titrant. The titration reaction is HCl-AQ plus NaOH-AQ sodium chloride AQ plus H2OL. What is the molarity of the HCl? Solution. As for all reaction stoichiometry calculations, the key issue is the relation between the molar amounts of the chemical species of interest as depicted in the balanced chemical equation. The approach outlined in previous modules of this chapter is followed, with additional considerations required, since the amounts of reactants provided and requested are expressed as solution concentrations. For this exercise, the calculation will follow the following outlined steps. This figure shows 4 rectangles. The first is shaded lavender and is labeled volume of NaOH. This rectangle is followed by an arrow pointing right, which is labeled molar concentration, to a second rectangle. This second rectangle is shaded pink and is labeled moles of NaOH. This rectangle is followed by an arrow pointing right, which is labeled stoichiometric factor, to a third rectangle which is shaded pink and is labeled moles of HCl. This rectangle is followed by an arrow labeled solution volume, which points right to a fourth rectangle. This fourth rectangle is shaded lavender and is labeled concentration of HCl. The molar amount of HCl is calculated to be 35.23 milliliters NaOH times 1L1000 ml times 0.250 moles. NaOH 1L times 1 mole HCl 1 mole NaOH equals 8.81 times 10 minus 3 moles HCl. Using the provided volume of HCl solution and the definition of molarity, the HCl concentration is M equals mole HCl solution M equals 8.81 times 10 minus 3 moles HCl 50.00 milliliters times 1L 1000 mLm equals 0.176 m. Note: for these types of titration calculations, it is convenient to recognize that solution molarity is also equal to the number of millimoles of solute per milliliter of solution. M equals mole solid L solution times 103 mol 103 mL equals mmol solute ml solution. Using this version of the molarity unit will shorten the calculation by eliminating two conversion factors. 35.23 milliliters NaOH times 0.250 mmol NaOH ml NaOH times 1 mmol HCl1 mmol sodium hydroxide 0.00 milliliters solution equals 0.176 mHCl. DL mmol. Check your learning. A 20.00 ml sample of aqueous oxalic acid, H2C2O4, was titrated with a 0.09113 m solution of potassium permanganate. Potassium permanganate. See net ionic equation below. 2MnO4 minus Aq plus 5 hydrogen oxalate, Aq plus 6H plus Aq10CO2 G plus 2Mn2 plus Aq plus 8H2OL. A volume of 23.24 milliliters was required to reach the endpoint. What is the oxalic acid molarity? Answer: 0.2648 m. Gravimetric analysis. A gravimetric analysis is one in which a sample is subjected to some treatment that causes a change in the physical state of the analyte that permits its separation from the other components of the sample. Mass measurements of the sample, the isolated analyte, or some other component of the analysis system, used along with the known stoichiometry of the compounds involved, permit calculation of the analyte concentration. Gravimetric methods were the first techniques used for quantitative chemical analysis, and they remain important tools in the modern chemistry laboratory. The required change of state in a gravimetric analysis may be achieved by various physical and chemical processes. For example, the moisture-water content of a sample is routinely determined by measuring the mass of a sample before and after it is subjected to a controlled heating process that evaporates the water. Also common are gravimetric techniques, in which the analyte is subjected to a precipitation reaction of the sort described earlier in this chapter. The precipitate is typically isolated from the reaction mixture by filtration, carefully dried, and then weighed, figure 4.17. The mass of the precipitate may then be used, along with relevant stoichiometric relationships, to calculate analyte concentration. A photo is shown of a flask and funnel used for filtration. The flask contains a slightly opaque liquid filtrate with a slight yellow tint. A funnel, which contains a bright yellow and orange material, sits atop the flask. The flask is held in place by a clamp and is connected to a vacuum line. The connection between the funnel and flask is sealed with a rubber bung or gasket. Figure 4.17. Precipitate may be removed from a reaction mixture by filtration. Gravimetric analysis. A 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of Ba, number 3, 2, resulting in the precipitation of 0.6168 grams of barium sulfate. Magnesium sulfate Aq plus barium nitrate 2, Aq barium sulfate, S, plus magnesium nitrate 2, Aq. What is the concentration, mass percent, of magnesium sulfate in the mixture? Solution. The plan for this calculation is similar to others used in stoichiometric calculations, the central step being the connection between the moles of barium sulfate and magnesium sulfate through their stoichiometric factor. Once the mass of magnesium sulfate is computed, it may be used along with the mass of the sample mixture to calculate the requested percentage concentration. This figure shows 5 rectangles. The first is shaded yellow and is labeled mass of BaSO subscript 4. This rectangle is followed by an arrow pointing right to a second rectangle. The arrow is labeled molar mass. The second rectangle is shaded pink and is labeled moles of BaSO subscript 4. This rectangle is followed by an arrow pointing right to a third rectangle. The arrow is labeled Stoichiometric factor. This third rectangle is shaded pink and is labeled moles of MgSO subscript 4. This rectangle is followed by an arrow labeled molar mass, which points downward to a fourth rectangle. This fourth rectangle is shaded yellow and is labeled mass of MgSO subscript 4. This rectangle is followed by an arrow labeled sample mass, which points left to a fifth rectangle. This fifth rectangle is shaded lavender and is labeled %MgSO subscript 4. The mass of magnesium sulfate that would yield the provided precipitate mass is 0.6168 grams barium sulfate times 1 mole barium sulfate 0.4, 3 grams barium sulfate times 1 mole MgSO 41 moles barium sulfate times 120.37 grams MgSO 41 moles magnesium sulfate equals 0.3181 grams magnesium sulfate. The concentration of magnesium sulfate in the sample mixture is then calculated to be % magnesium sulfate equals mass magnesium sulfate mass sample times 100%, 0.3181 grams, 0.4550 grams times 100% equals 69.91%. Check your learning. What is the percent of chloride ion in a sample if 1.1324 grams of the sample produces 1.0881 grams of silver 1 chloride when treated with excess Ag plus AQ plus Cl minus AQ AgClS? Answer: 23.76%. The elemental composition of hydrocarbons and related compounds may be determined via a gravimetric method known as combustion analysis. In a combustion analysis, a weighed sample of the compound is heated to a high temperature under a stream of oxygen gas, resulting in its complete combustion to yield gaseous products of known identities. The complete combustion of hydrocarbons, for example, will yield carbon dioxide and water as the only products. The gaseous combustion products are swept through separate pre-weighed collection devices containing compounds that selectively absorb each product. Figure 4.18. The mass increase of each device corresponds to the mass of the absorbed product and may be used in an appropriate stoichiometric calculation to derive the mass of the relevant element. This diagram shows an arrow pointing from O subscript 2 into a tube that leads into a vessel containing a red material, labeled sample. This vessel is inside a blue container with a red inner lining which is labeled furnace. An arrow points from the tube to the right into the vessel above the red sample material. An arrow leads out of this vessel through a tube into a second vessel outside the furnace. And a line points from this tube to a label above the diagram that reads CO subscript 2, H subscript 2O, O subscript 2, and other gases. Many small green spheres are visible in the second vessel, which is labeled below H subscript 2O absorber, such as Mg, ClO, subscript 4, subscript 2. An arrow points to the right through the vessel, and another arrow points right heading out of the vessel through a tube into a third vessel. The third vessel contains many small blue spheres. It is labeled CO subscript 2 absorber, such as NaOH. An arrow points right through this vessel, and a final arrow points out of a tube at the right end of the vessel. Outside the end of this tube at the end of the arrow is the label O subscript 2 and other gases. Figure 4.18. This schematic diagram illustrates the basic components of a combustion analysis device for determining the carbon and hydrogen content of a sample. Example 4.16. Combustion analysis. Polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. A combustion analysis of a 0.00126 gram sample of polyethylene yields 0.00394 grams of CO2 and 0.00161 grams of H2O. What is the empirical formula of polyethylene? Solution. The primary assumption in this exercise is that all the carbon in the sample combusted is converted to carbon dioxide, and all the hydrogen in the sample is converted to water. CX plus excess O2G x CO2G plus Y2H2O of G. Note that a balanced equation is not necessary for the task at hand. To derive the empirical formula of the compound, only the subscripts X and Y are needed. First, calculate the molar amounts of carbon and hydrogen in the sample, using the provided masses of the carbon dioxide and water respectively. With these molar amounts, the empirical formula for the compound may be written as described in the previous chapter of this text. An outline of this approach is given in the following flowchart. This figure shows two flowcharts. The first row is a single flowchart. In this row, a rectangle at the left is shaded yellow and is labeled mass of CO subscript 2. This rectangle is followed by an arrow pointing right to a second rectangle. The arrow is labeled molar mass. The second rectangle is shaded pink and is labeled moles of CO subscript 2. This rectangle is followed by an arrow pointing right to a third rectangle. The arrow is labeled stoichiometric factor. The third rectangle is shaded pink and is labeled moles of C. This rectangle is followed by an arrow labeled molar mass, which points right to a fourth rectangle. The fourth rectangle is shaded yellow and is labeled mass of C. Below is a second flowchart. It begins with a yellow shaded rectangle on the left, which is labeled mass of H subscript 2O. This rectangle is followed by an arrow labeled molar mass, which points right to a second rectangle. The second rectangle is shaded pink and is labeled moles of H subscript 2O. This rectangle is followed by an arrow pointing right to a third rectangle. The arrow is labeled stoichiometric factor. The third rectangle is shaded pink and is labeled moles of H. This rectangle is followed to the right by an arrow labeled molar mass, which points to a fourth rectangle. The fourth rectangle is shaded yellow and is labeled mass of H. An arrow labeled sample mass points down beneath this rectangle to a green shaded rectangle. This rectangle is labeled percent composition. An arrow extends beneath the pink rectangle labeled moles of H to a green shaded rectangle labeled C to H mole ratio. Beneath this rectangle, an arrow extends to a second green shaded rectangle which is labeled empirical formula. Mole C equals 0.00394 grams CO2 times 1 mole CO2 44.0. 1 grams times 1 mole C. 1 mole CO2 equals 8.95 times 10 minus 5 moles. C a mole H equals 0.00161 grams H2O times 1 mole H2O 1. 8.02 grams times 2 moles H. 1 mole H2O equals 1.79 times 10 minus 4 moles H. The empirical formula for the compound is then derived by identifying the smallest whole number. The H to C molar ratio is m mole. H m mole C equals 1.79 times 10 minus 4 moles H. 8.95 times 10 minus 5 moles C equals 2 moles H. 1 mole C. And the empirical formula for polyethylene is CH2. Check your learning. A 0.00215 gram sample of polystyrene, a polymer composed of carbon and hydrogen, produced 0.00726 grams of CO2 and 0.00148 grams of H2O in a combustion analysis. What is the empirical formula for polystyrene? Answer: CH